stellar mass black holes. The most common type begins at the level of stars. When a star with enough mass burns through its fuel and collapses, the outer layers can explode in a supernova, while the core falls inward on itself. If the star was heavy enough, nothing halts the collapse. That is the birth of a stellar mass black hole. These objects typically weigh between 5 and a few dozen times the mass of our Sun. At first glance, that may not sound dramatic. The Sun is already huge compared to Earth. Yet in the black hole hierarchy, a few solar masses is just the entry fee. Their diameters, defined by the event horizon, are tiny on a cosmic scale, sometimes only tens of kilometers wide. Picture an entire star's mass squeezed into the footprint of a city. What matters is not size in kilometers, but the density and the escape velocity. Even at the smallest level, gravity is so intense that light cannot escape. Stellar black holes are the hidden leftovers of violent stellar deaths. They roam the galaxy invisibly, revealed only when matter falls into them or when they merge and send out bursts of gravitational waves. Destructive power scales with feeding. A quiet stellar black hole is almost harmless if nothing gets too close. But if a companion star drifts within range, the black hole can strip gas from it, spinning that gas into an accretion disk that heats to millions of degrees. In X-rays, these systems blaze across the sky. There is still a debate about how big a stellar black hole can get before moving into a new category. Observations in our own galaxy have confirmed some that tip the scales at 20 or 30 solar masses. With improved instruments, astronomers have even spotted stellar black holes in other galaxies crossing 70 or 80 solar masses. These are rare and often the result of stars born in low-metal environments where stellar winds are weak, allowing the star to keep more mass before collapsing. When you picture black holes as cosmic predators, these are the small hunters. Their reach is local, affecting their immediate surroundings. But their mergers matter. The signals recorded by detectors like LIGO and Virgo come mostly from collisions between stellar mass black holes. When they smash together, the new black hole can leap in size, giving a clue to the bridge toward the next category: intermediate mass black holes. For years, scientists wondered if a gap existed between the common stellar variety and the giant ones at galaxy centers. That middle ground would be occupied by intermediate mass black holes. They are predicted to weigh anywhere between hundreds and hundreds of thousands of solar masses. Evidence for them has always been slippery. Unlike stellar black holes, they are not easily caught in binary systems. And unlike supermassive black holes, they don't anchor galaxies that give away their presence. Instead, astronomers chase hints in star clusters and dwarf galaxies. One method is tracking the orbits of stars moving suspiciously fast in tight circles, a sign of an unseen massive object pulling them around. One confirmed candidate is HLX-1 in a galaxy about 300 million light-years away. Its outbursts and X-ray profile suggest a black hole weighing around 20,000 solar masses. Other possible examples hide in globular clusters, dense knots of old stars orbiting larger galaxies. These environments provide enough crowding for runaway collisions, which may eventually form an intermediate black hole. But why do they matter? Because they solve the puzzle of growth. Supermassive black holes at galaxy centers exist even in the early universe. That raises the question, how did something reach billions of solar masses so quickly? Intermediate black holes may have acted as stepping stones, swallowing matter and merging until they reach supermassive scales. Without this missing link, the timeline seems too short. In terms of destructive scale, an intermediate black hole is far more dangerous than a stellar one. Its tidal forces can rip apart stars whole, producing violent events known as tidal disruption flares. The reach of its gravity covers a wide portion of a star cluster, altering orbits and dynamics. These middleweights are not common predators, but if you were in a dense cluster where one lurks, you would be living in its gravitational web. As black holes grow in mass, their event horizons expand proportionally. A stellar mass black hole of 10 solar masses might have a horizon only 30 kilometers across. An intermediate black hole with 100,000 solar masses could stretch hundreds of thousands of kilometers. The difference is more than size. It is how far-reaching the gravitational dominance becomes. The larger the mass, the gentler the tidal forces near the horizon. This leads to one of the strange consequences of scale. A stellar mass black hole would spaghettify a human long before they reach the horizon, while a supermassive one might let you cross the event horizon without immediate tidal destruction. Size does not just change strength, it changes the way that strength is applied. The road to the giants. Part of why intermediate black holes fascinate astronomers is that they could be the seeds that grow into supermassive black holes. Stellar black holes collide, forming heavier remnants. Over time, those remnants sink to the dense center of a cluster where they merge again. With enough collisions and gas feeding, the object tips into intermediate scale. Once that threshold is crossed, runaway growth becomes easier. Gas inflow, mergers with other clusters, and gravitational attraction all contribute to a snowball effect. To understand scale, it helps to compare in numbers. A stellar black hole at 10 solar masses packs its horizon into a sphere about 30 kilometers wide. That is small enough to fit into Earth's geography. An intermediate black hole at 100,000 solar masses has a horizon about the size of Jupiter. Both are invisible, but their influence differs wildly. If a stellar black hole wandered into the solar system, it would certainly wreak havoc locally, but its range would not control every planet at once. An intermediate black hole of 100,000 solar masses, on the other hand, could reshape entire planetary systems and bend the orbits of stars. These comparisons highlight the hierarchy clearly. The scale is not linear. Moving from tens of solar masses to hundreds of thousands represents a leap of several orders of magnitude. Each step up in this ladder multiplies destructive power in ways that dwarf the step before. Modern observations with gravitational wave detectors, space telescopes, and high-resolution galaxy surveys are making the hierarchy clearer. Stellar black holes are confirmed, abundant, and constantly merging. Intermediate black holes remain the hardest to prove, but show up in more candidate signals every year. The pattern is becoming visible. Small black holes dominate in numbers, but rare larger ones shape the fate of systems, clusters, and ultimately galaxies. Supermassive black holes. Every large galaxy we have studied carefully enough contains a supermassive black hole at its center. Their mass starts at a few million suns and can reach billions. The Milky Way's central black hole, Sagittarius A, is on the smaller side at around 4 million solar masses. In comparison, some galaxies host black holes thousands of times heavier. Despite their scale, they do not announce themselves with fireworks unless actively feeding. When a steady stream of gas falls inward, the process ignites quasars, the brightest objects in the universe. Disks of gas swirl near the event horizon, heated by friction to temperatures that produce radiation powerful enough to outshine entire galaxies. At their peak, billions of years ago, quasars were visible across cosmic distances, serving as lighthouses from the young universe. Even a quiet supermassive black hole has influence. The orbits of stars near galactic centers trace their pull. Stars whip around invisible points, with velocities too fast to be explained by anything else. The presence of these giants is so consistent that they have become a fundamental piece of how galaxies are understood. The destructive ability of supermassive black holes is best understood by comparing them to their smaller relatives. A stellar black hole can shred a star by pulling more strongly on one side of it than the other. In contrast, a supermassive black hole's event horizon is so large that the tidal gradient at the horizon is weaker. This means you could cross the boundary without immediate spaghettification. The lethal forces occur deeper in, but when entire stars stray too close, even these giants pull them apart. A tidal disruption event sends stellar debris into an orbiting disk, releasing a burst of radiation that astronomers can detect from across galaxies. These events prove that even the largest black holes still act as destroyers, though on timescales and scales far greater than human imagination. Some of the heaviest known black holes go beyond the standard definition of supermassive. These are sometimes called ultramassive black holes. They sit in the centers of galaxy clusters, weighing tens of billions of solar masses. The record holders, found in brightest cluster galaxies, reach around 40 billion solar masses. At that level, the event horizon could stretch wider than our entire solar system. Imagine the orbit of Neptune swallowed inside one object. The volume of space controlled by gravity at that scale is so immense that it alters not just a galaxy, but the cluster around it. When these ultramassive black holes feed, they do not merely release jets, they can carve cavities in the hot plasma of galaxy clusters. Radio observations revealed giant voids where jets have pushed material aside over millions of years. These cavities span hundreds of thousands of light years, dwarfing individual galaxies. Growth beyond imagination. How do black holes grow so large in the time the universe has allowed? Gas accretion alone seems too slow. The best explanation is a combination of rapid early feeding, frequent mergers, and the possibility that the seeds they grew from were already large. If intermediate black holes were born early in dense stellar clusters, their mergers could quickly jumpstart the growth. In the most distant galaxies observed, astronomers have already detected quasars powered by billion solar mass black holes less than a billion years after the Big Bang. That is uncomfortably fast under traditional models. To explain it, some theories propose direct collapse, where a massive cloud of gas falls inward without first fragmenting into stars, leaving behind a massive black hole seed. The exact answer is still debated, but what matters is that the universe had a way of producing giants early, and those giants shaped everything that followed. Supermassive black holes are not passive sinks. Their activity regulates star formation. When they feed heavily, they drive outflows and jets that heat or expel the surrounding gas. Without cold gas, new stars cannot form. This feedback process may sound destructive, but it creates balance. It prevents galaxies from forming too many stars too quickly, which would exhaust their gas supplies prematurely. In this sense, black holes are paradoxical. They are engines of destruction, swallowing everything that dares to approach too closely. Yet they are also stabilizers, setting the pace at which galaxies mature. Without them, the structure of the universe would look entirely different. Comparing scales, to feel the magnitude of difference, line up the categories. A stellar mass black hole of 10 suns is only about 30 kilometers across. An intermediate black hole of 100,000 suns has a radius on the scale of Jupiter. A supermassive black hole of 1 billion suns extends past the orbit of Mercury. An ultramassive black hole of 40 billion suns would swallow every orbit in our solar system and still have room. The destructive range is not limited to the event horizon. Gas inflows, jets, and winds can spread thousands of light years. A single outburst from a feeding supermassive black hole can regulate an entire galaxy's evolution for millions of years. Is there a ceiling to black hole size? Simulations suggest that above a certain mass, accretion becomes inefficient. The black hole heats its surroundings so strongly that incoming matter is pushed away. This creates a feedback loop that caps growth at around 50 billion solar masses. Some estimates extend the possible maximum slightly higher, but beyond that, stability becomes questionable. No confirmed black hole heavier than this has been found, though the search continues. The largest candidates known so far remain within the theoretical limit. This implies that cosmic processes do indeed enforce natural caps, preventing black holes from consuming everything unchecked. destruction and creation. The destructive image of black holes often overshadows their creative role. They annihilate anything too close, but they also energize galaxies, stir up matter, and prevent runaway star formation. Their growth charts the history of cosmic structure, from the first seeds in the early universe to the massive engines of today's galaxy clusters. Black holes form the backbone of how the universe organizes itself. Humanity lives far from this chaos, on the galaxy's calm outer arms. If Earth were close to the galactic core, our night sky would be filled with bright stars whipped into tight orbits. Life would evolve under the constant background of a supermassive black hole's presence. At our distance, it is a quiet fact of existence, hidden behind dust and distance, yet still central to the galaxy's structure. New detections of mergers, sharper telescope images, and deeper surveys keep revealing more about the middle ground and the extremes. Each discovery locks in another rung of the ladder, showing us how something as simple as collapsed matter can define the architecture of the cosmos.